First of all, in your volume 4 on page 141, at the top you've got a table C.1. That does not say anything about rock. However, in the Bridge Design Manual version of that table, the first note will give the fee factor of 0.70 for driving to rock. So that will be in the Bridge Design Manual. That number, as I believe was mentioned by one of the other speakers, is really just our 0.725 rounded to an even fraction. Also, we have an example in your volume 4, starts on page 60, which is a case where the pile is driven to rock. And not only that, but we're picking up some friction up above the rock. So it's got both the friction above the rock as well as bearing on rock. One of the questions that we've tossed around among ourselves is, should we have some sort of a limit? If your friction capacity is less than a quarter of the total, do you just forget about it and only go to the rock? We haven't made any kind of decision on that. The example shows the actual use of the friction plus the end bearing. So, rock will be covered in the Bridge Design Manual. It's also in your volume 4 in that track 1, example 5. So far, if you've looked at that chart that I talked about, and we've talked about the Blue Book, you notice you go down on the left, there's the timber pile, then there's the H pile, and pre-stressed and pipe. Well, anyway, you go to the table or chart and you keep going over, and we've got 2 more pile types there. Basically, bottom line, what we've decided to do is use exactly the same fee factors for those 2 pile types, the pre-stressed and the pipe pile that's closed when it's driven and filled with concrete. This kind of is a simple table showing the various pile types, the various uses that you would have, and then the blocks with the asterisks are where we actually have standard sheets that you can get to on our website, where we've pre-detailed certain standard conditions. We do not use or recommend either pre-stressed piles or the pipe piles for integral abutments. There was one county project where it was tried as part of an Iowa State research project to use pre-stressed concrete piles in an integral abutment. And they found some annoying cracking down below the abutment when they dug in and checked it. So that's kind of been tried, and it doesn't look good. So we don't recommend it, and we don't recommend the steel pipe either. The only case where we would use a timber pile bent would be in a temporary condition. We would not use that in a permanent condition. Just going back to the basic LRFD relationship, what I'm going to be doing is going through all of the different pile types and indicating where you would find the information that you would need for design. I'm going to start with the left side of the equation, work toward the right side, and at the end, hopefully I'll have kind of gone through the last sheet that you have in your workbook. First of all, for all of the pile types, all of the loads And load factors we get from AASHTO except for down drag. For down drag, we use a load factor of 1.0. AASHTO, I think, has a couple of options there. The 1.0 comes from some of our trials over about the past 10 years. We tried different things under allowable stress design, and this comes closest to what generally worked. It's not exactly the same, but it seems to be okay at this point. For the steel H piles, we have set up 3 different structural resistance levels. Basically, what we're doing is saying 6 KSI, 9 KSI, and 12 KSI. So we're going back and sort of camouflaging allowable stress design with those resistance levels. But they work out to approximately the same as the allowable stress levels. For integral abutments, we limit it to SLR2, approximately 9 KSI. That allows some capacity for moment at the head of the pile as the pile would flex. We also have put in some simplified allowable, or in the case of load and resistance factor design, nominal values for shear, and that is intended to be at the top of an embedded pile. That question came up yesterday. Can you use that if the pile is extended above the ground? And the intent is not. That I think that value that has been used in the past under allowable stress design probably was intended for our so-called stub abutments, where we've got some kind of lateral load, and we don't want to go to a lot of analysis to figure out exactly how things work. The intent of that is for ordinary conditions. If you have a specific lateral deflection limit, you should go and do your own analysis, because that may not be a good number. Phi factors for the structural use would be from AASHTO. For the timber piles, we've again gone back to our past practice, converted the previous ton values for piles, 64 kips for the shorter timber piles, 80 kips for the longer ones. Integral abutments, limit is 64 kips. And we also have a permissible resistance for the lateral load. Phi values, again, would come from AASHTO. And that, of course, is for the structural conditions. In the case where we have kind of pre-designed pile bents, set up the P10L sheet, which used to be a P10A. We've set that up so that you can just design for a vertical load. We've set the limits and everything so it covers an ordinary amount of moment and so forth in the pile. We've set that up for the H-pile, pre-stressed, and pipe piles. There's basically a maximum height above ground stream bed or design scour that's intended to make sure the pile doesn't buckle. If you get too tall, you got a problem. We also have a minimum embedment that is intended to prevent a fence post type of failure. The intent of the failure is that it should be a flexural failure rather than just kind of fall over. And those values, besides being given on the P10L sheet, are in the design manual. Now, when it comes to the geotechnical work, we're using the research, translating it as we can to our use. And those bridge design manual tables, generally you've got the versions of them in the volume 4, but we're modifying those as necessary. For the driving target, again, there will be a table in the bridge design manual, similar to the tables that have been used today. Just point out again that we have a relatively low target value for timber piles for driving purposes. And then this is the screen version of that last sheet that you have. And what I've tried to do there is go down the first column, list the various factors about the top 60% of the table or thereabouts are structural, then geotechnical, and the driving resistance for each of the different pile types. And where you see the gray stuff, well, we don't got any information on that. If you want to use something under those conditions, you're on your own. You need to get some information, or in the case of the integral abutment condition, we definitely don't recommend pre-stressed or concrete-filled pipe pile. There are a few cases where those bridge design manual sections refer to what's going to be the future manual. In some cases, the information won't change, but just to caution you, if you go to the abutment section or the pier section, we haven't got the drafts ready yet. They should come out in January, and so they'll be revised to fit. In general, where we've got typical bridges and we've done some pre-design, or in the case of using the Iowa State research, use the bridge design manual. If nothing is available, it means that we're basically not supporting it. You can go back to AASHTO if it's a reasonable thing. If it's like pre-stressed piles for a integral abutment, you know, there's a reason why we didn't give any information on that. Before I ask for questions, and I think this will probably generate some questions, I went to, this is almost 2 years ago now, I took the boring logs from the pile driving on 5 of the Iowa State sites. And one of the sites, the piles were driven all the way to rock. They weren't tested down to rock. The Iowa State tests always stopped short of rock. But one of the actual projects, the designer had the piles driven to rock. 2 of the sites were clay, 2 mixed. One of the things that became apparent is that under our old system, the allowable stress system for driving using WEEP analysis, there was quite some variation in how soon bearing was reached. The minimum I've got down here is about 55% of the pile length. In other words, they drove the pile about halfway and they had bearing. There were cases, though. There was one case where they had to do a retap, 1 out of 14 substructure units. There were 3 cases where they had to go to 90% of the pile length before they got bearing. And I believe it was also in one of the pile logs that I've looked at. What was really weird is they reached bearing at about 1/3 of the pile length, and then they lost it as they continued to drive, and they didn't reach bearing until they got the whole pile in. So there are funny things that happen during driving. And it looked like in these cases, generally, if you take an average, and this of course is a very small sample, it took about 84% of the plan length to get bearing for abutments and about 69% of length to get the bearing for piers. So piers reach bearing a little bit quicker than the abutments. But when you look at the typical bridge profile, you know, imagine where the tips are. It varies. So there's a lot of variation there, and we're kind of interested in how the LRFD system works out. It appears that probably the drivers will be reaching bearing for the 3 of the pile types, will be reaching bearing earlier than otherwise. Now, a question that has been kind of talked about among some of the people here is, what is this LRFD going to do to our pile lengths? In this, you know, very simple sample, or very small sample, and not the final work, it looked like if you're not driving the rock, it's maybe 10% at most. There's some variation in there, but there's likely to be some difference. You can go back to what our equivalent allowable stress factor would have been, which was 0.725 versus 0.65, 0.6, or 0.55, and you can see that that's probably going to lengthen the piles. Now, it's not going to lengthen them quite as much as you might expect, because the better soil tends to be down there. So if you need another 10% capacity, you don't necessarily have to drive 10% of your pile, because, you know, a lot of this stuff up near the top is junk. You're not getting anything out of it anyway, and it's only when you get down near the bottom that you start picking up bearing pretty quick. So we're expecting that the pile lengths will increase a little bit. Now, if you look at the overall way that we've approached it and play professor with it a little, as I used to do, what we've done is we've said, okay, you get your loads, factor them up, and that tells you how many piles you have. And then you go and you figure out how long they got to be, and, you know, deal with the driving. Well, suppose you've got a site that doesn't have real good capacity and you want to kind of look at things otherwise. What you could do is say, okay, what can I get out of this pile if I drive at 60 feet? And figure backwards, and then decide on your number of piles based on the load that you have to meet from the superstructure and substructure, and what you can get out of the pile. So you don't necessarily have to work everything in exactly the sequence that we talked about today, but in our office we tend to do it that way. I'm sure the consultants have probably got a few more bag of tricks out there for unusual situations where you don't necessarily work the problem from top down, that you may work it in the reverse way.